Dear students, today we begin our first lecture from the Analytical Chemistry of the second semester. The name of our first lecture is Quantitative Analysis. Quantitative analysis is the determination of the absolute or relative abundance, often expressed as a concentration of one, several or all particular substance present in a sample. Quantitative analysis divided into two parts, as we see from the table. The first is volumetric analysis. Second is gravimetric analysis. Is chemical analysis. In the volumetric analysis, a solution of B at known concentration is added to a known volume of A until the number of the equivalent of B is equal to zeros of A. The added volume of B is measured and the concentration of A can be calculated. In the other word, volumetric analysis is based on the determination of the measurement of the volume of the reagent consumed for the interaction with the analyzed sample. Gravimetric analysis is based, as we see, on the chemical reaction like the volumetric analysis. In this case, an excess of B at unknown concentration is added to A so that A is completely transformed in C that can be weighted. The gravimetric analysis, in the other word, based on measurement of the accurate weight, accurate mass of the sample, analyzed sample. There are three basic principles of quantitative definition. The first, measurement of the physical properties of the substance or products of the chemical reaction. The first physical properties, for example, density. We use the density for the solutions, for the liquids. Other physical properties is a color, different color of the solutions, and electrical conductivity of the solutions, and other. The second, measurement of amount of the product of the chemical reaction of the substance with any reagent by weight of sediment, gas, volume, for example. For example, to determine of barium ion in the composition of barium chloride, it is completely precipitated by sulfate anion quantitatively. The resulting solution is filtered and dried to constant weight, and we have the reaction, chemical reaction. It is a precipitation of barium ion with a sulfite anion and precipitation form barium sulfate. Then determine the mass of the sample, the mass of the precipitation form. We use the proportion method. By the proportion molecular weight of the barium sulfate precipitation form to molecular weight of barium ions and molecular weight of the A substance. A here is the barium chloride, initial substance, and X, we find X weight of the barium anion, because barium anion is a determinate anion, a determinate functional group. Here X equal A multiplied molecular weight of barium anion and divide molecular weight of precipitation form. Third, measurement of the volume of the reagent, gas or reagent solution consumed for chemical interaction with the substance to be determined. For example, the reagent solution is added in a small portion and establishes the equivalent point of the chemical reaction. In the picture, we can see the titration process in which from the burette, it is a vessel, a chemical vessel, drop by drop add titrant solution to the analyzed sample. In this case, for example, acid of unknown concentration. And we use in the titration method, as usually for detection of equivalent point, is use some indicators. Analytical methods can be separated into classical and instrumental method. As we see before, classical methods, for example, gravimetric analysis, classical chemical methods, gravimetric analysis, volumetric analysis, and for instrumental methods, we know we use the apparatus to measure the physical quantities of the analyte, such as light absorption, fluorescence, or conductivity. And from these methods, we know spectroscopy, electrochemistry, chromatography, and other methods. Gravimetric analysis, it's one type of the chemical analysis. As we say before, it's based on the measurement of the accurate weight of the analyzed sample. In this method, gravimetric analysis, there are used the other methods which we use in gravimetric analysis. For example, precipitation method is most common used in this gravimetric analysis, and we see from the picture there are different steps of the gravimetric analysis. Steps, for example, at first is taking of the sample, second step is weighting of the sample, third is dissolution, next step precipitation, other step after precipitation we have filtration, washing of the precipitation, then we have washing of the precipitation, after we have drying, we have ignition. At last we calculate the results of the analysis. Volumetric analysis, as we said before, it is a general term for the method in quantitative chemical analysis in which the amount of substance is determined by the measurement of the volume that the substance occupies. It is commonly used to determine the known concentration of a known reactant. Volumetric analysis is often referred to as titration, a laboratory technique in which one substance of unknown concentration and volume is used to react with another substance of unknown concentration. Titrometric analysis. The term titrometric analysis refers to quantitative chemical analysis carried out by determining the volume of the solution of accurately known concentration, which is required to react quantitatively with the measured volume of the solution of a substance to be determined. The solution of accurately known concentration is called standard solution. Titer, meaning the concentration of substance in grams in 1 milliliter of solution. Titer is the concentration of the solution. The exact concentration region solution used in titrometric analysis are called titrants, or secondary standard or working solutions. The concentration of titrants is established using special substances with suitable chemical properties, consistency of the composition, stability, and called standards, or in other primary standards. Determination of bases. Titrant solution. For determination of the bases, as titrant solution is used hydrogen chloride solution and determined according to an exact weight of the standard primary standard, sodium carbonate or sodium tetraborate. Sodium carbonate and sodium tetraborate are primary standard solutions, which we used for determination of exact concentration of hydrogen chloride solution. Determination of the point of equivalence in titrometric analysis is carried out by titration, the gradual addition of the titrant to the solution of the analyte. The equivalent point is fixed using the chemical or instrumental indicators. Chemical indicators change their color depending on pH, redox potential, when an excess of reagent appears in a solution or the analyte disappears. For example, from the table, we can see pH of the different indicators in the which have the different colors. For example, universal indicator is in acidic medium, it's red. In neutral, it's green. In basic medium, in alkali medium, it is purple. Phenolphthalein, it's in neutral medium. In neutral medium, it is colorless. In acidic medium, it is colorless. In alkaline medium, it is purple. Methyl orange, in neutral medium, it's orange or red. In acidic medium, it's yellow, and in basic medium, it's yellow. Thymol blue, it's is pink in neutral medium. It's in acidic medium, it is yellow, and in basic medium and alkaline medium, it's blue, and other. There are four main types of titration: acid-base titration, complexometric titration, precipitation titration, and redox titration. Acid-base titration, in which an acidic or basic titrant reacts with an analyte that is a base or an acid. Complexometric titration, involving a metal-ligand complexation reaction. Precipitation titration, as we see from the name, in which the analyte and titrant react to form a precipitate. Redox titration, where the titrant is an oxidizing or reducing agent. There are three types of titration, three ways of titration: direct titration, back titration, and substitution titration. For example, sodium chloride in solution can be determined by back titration, adding to its solution an excess of the titrant 1, first titrant. First titrant is silver nitrate, and titrating the unreacting part of the silver nitrate with a second titrant solution, ammonium rhodanate or ammonium thiocyanate. The amount of silver nitrate solution, V, consumed on interaction with sodium chloride is determined by the difference between its added volume V1 and volume V2 retitrated volume, titrated with a solution of ammonium rhodanate. And the reactions we can present in this form by two reactions. The first reaction, in the first reaction we can see that for determination of sodium chloride, silver nitrate is added to sodium chloride in excess and form silver chloride precipitate. Then the excess of the silver nitrate solution retitrated with a second titrant solution, ammonium rhodanate. For example, example of the substitution titration. For example, potassium bichromate is determined by adding potassium iodide and sulfuric acid. Sulfuric acid is a medium process reaction. Free iodine released by the oxidation reduction reaction is titrated with a sodium thiosulfate solution. This is substitution titration. In this reaction, amount of the potassium bichromate solution is substituted on the quantitatively substitute on the amount of freeodine solution, which is possible titration, back titration, direct titration, and formed released freeodine by addition of the indicator. Indicator in this method is colloidal starch solution. By addition of starch solution to the freeodine solution, which is released on the quantitatively from the reaction, form blue color, and we titrate freeodine, which is released in the conical flask, with a sodium thiosulfate tetrane solution, which is in the burette, and at the equivalent point, blue color of the freeodine disappears. Acid-base titration, it's a type of the titration, first type of the titration. Acid-base titration methods, as we say before, are based on the use of the reaction between acids and bases. In the other word, we call this method a neutralization method. In general, this reaction can be represented by the two equations. In this case, oxonium ion is an acid, B, it's a base, salt, and solvent, water. Acid, oxonium ion, plus base, and water is a solvent. Acid-base titration. Acid-base titration is divided into two parts, on acidometric and alkalimetric. In acidometric titration, as we see from the name of the method, acetate solutions used acids, hydrogen chloride and sulfuric acid. In alkalimetric titration, acetate solutions used alkalis, sodium hydroxide and potassium hydroxide. All titrants are secondary standard solutions, therefore demand of standardization, definition of precise concentration. So for this purpose we have to use primary standard solution. Acidometric titration is used to determine strong and weak bases, basic salts, salts of weak acids, and organic compounds with basic properties. When titrating strong bases with acid solutions, at the moment of the equivalence, water and neutral salt are obtained. The solution has a neutral reaction. For example, strong base, it's a strong base which have a hydroxide group. We can represent this by these reactions. Strong base sodium hydroxide plus hydrogen chloride here form salt and water, and pH of the medium is equal 7. If a weak base is titrated, for example ammonium, occurs neutralization reaction of a weak base with a strong acid. For example, weak base ammonium anion, ammonium cation, plus water, here form ammonium, free ammonia in gas, and hydroxonium ion, and the reaction we can represent it in this form: ammonium hydroxide plus hydrogen chloride form ammonium chloride, like this reaction, and form water. The resulting salt of a weak base undergoes hydrolysis. Hydrolysis, for example, ammonium chloride plus water, it is a hydrolysis reaction. Here form ammonium hydroxide and strong acid. as and the medium of the reaction pH less than 7. When titrating salt of weak acid, for example, sodium acetate, a weak acid is formed, and the reaction is represented in this form: acetate anion plus hydrogen proton form weak acid, and the reaction, it's a titration of the salt which formed from the weak acid and strong base. The reaction with a hydrogen chloride with a strong acid forms weak acid and salt, sodium chloride, and pH in this case less than 7. If a salt of a weak acid is formed by the polyprotonic acid, for example sodium carbonate, then during titration several points of equivalence are observed. For example, by addition of strong hydrogen chloride to trans solution to sodium carbonate to the primary standard solution, form sodium hydrocarbonate in the first equivalent point. In the second equivalent point, sodium hydrocarbonate continued titrated to titration with a hydrogen chloride, and in the second equivalent point, pH of the medium less than 7. For titration of the basic salts, for example, calcium hydroxychloride, the reaction represented in this form with a strong hydrogen chloride acid, and the pH equal 7. Organic bases. From the organic bases, for example, it's a radical NH2 amine, some amines, plus hydrogen in the second reaction are formed. The reaction of the medium at the equivalent point is neutral. For example, in the picture we can see the titration of the alkalometric titration. In this case, we can see that in equivalent point, in this case is used the phenolphthalein indicator, acid-base indicator phenolphthalein, which has changed the color from colorless into purple. For example, it is before titration, it's after titration at the equivalent point. Before titration, the solution is colorless. At the equivalent point, it is purple, as we see. Strong acids, for example, titration of strong acid hydrogen chloride with a titrant solution sodium hydroxide. pH of the medium is equal 7. When titrating weak acids such as acetic acid, acetate, ion is formed, which undergoes hydrolysis, as a result of which the reaction of the medium at the equivalent point becomes weakly alkaline. Weak acids, for example, titration of the weak acid, sodium acetic acid with a strong base with a sodium hydroxide, hydrolysis of the salt which formed from the weak acid and strong base, in this case pH of the medium more than 7. Acidic salts, for example, sodium hydrosulfate, when titrated form normal salts, for example sodium sulfate and water, and the equivalent point occurs in the neutral medium. Acidic salts, titration of the acidic salts, sodium hydroxysulfate with a titrant solution sodium hydroxide, pH of the medium equal 7. Salts of weak bases during titration with sodium hydroxide solution form a weak base which undergoes hydrolysis. For example, ammonium chloride with a strong sodium hydroxide form weak ammonium hydroxide base and pH of the medium more than 7. Organic acids are also capable of titration with sodium hydroxide solution, and the resulting anion of the acid reacts to hydrolysis and the medium becomes alkaline. For example, the titration of the organic acid sodium acetic acid with a sodium hydroxide, and hydrolysis of this salt formed during the reaction. It's the hydrolysis of this pH of the medium more than 7 because form free hydroxide group. The possibility of using acid-base titration is determined by the total equilibrium constant of the acid-base reaction, which should be greater than 1 multiplied 10 in 8 degree if the completeness of binding of the substance being titrated is 99.99% and its residue is 0.01% or 1 multiplied minus 4 degree of the initial amount taken as unit. We have the proportion 100 to 0.01 and 1 mole of this solution is X, and from this we can find X equal 10 minus 4 mole liter. And we can represent this by the equation hydrogen proton plus B anion form HB. It's some acids, and the concentration of this is equal 1. Concentration of the hydrogen proton is equal 10 minus 4. We found from this proportion, and concentration of the B anion is equal 10 minus 4 degree, the same. And the constant of the equilibrium we can find from the equation concentration of the acid divide on the concentration of hydrogen proton multiplied concentration of B minus, and from this we find that the constant of equilibrium is equal 10 8 by degree of 8. For example, based on the equilibrium constant, the formate ion cannot be completely titrated, and the phenolate ion can be. The formate ion plus hydrogen proton form formate acid, and the constant of the equilibrium in this case we can see from the calculation is equal 0.56 multiplied 10 in 4 degree, and the constant less than 10.8. The reaction is incomplete, cannot be titrated. The phenolate ion, for example, phenolate ion titration with a hydrogen proton, we can form phenols, and the constant of the equilibrium is equal 0.95 multiplied 10 in 10 degree. In this case, constant more than 10.8 and can be titrated. Determination of the equivalent point. It is possible to determine equivalent point by two ways, by the chemical indicators and by the physical-chemical methods. By the physical-chemical methods, we know the potentiometric titration, conductometric titration, photometric, spectrophotometric, amperometric methods. chemical indicators. There are two types of chemical indicators. For example, acid type indicators. In this case, we have hydrogen indicator, which is decomposite on hydrogen, positively charged hydrogen proton, negatively charged indicator. And in this case, constant of acidity we found from this equation. Base type of indicator, hydrogen proton with the indicator form, indicator hydrogen with a hydrogen proton, and constant of basicity we can find from this equation. Phenolic groups under the influence of an alkaline medium are capable of passing into henoate group. For example, phenolic group, it's passing into henoate group. Indicators, as we see from the before this, we say that the indicators change the color independence of the medium, independence of the pH and other parameters. Some indicators are better suited to different acid-base reaction. Indicators have the transition interval. It's a transition interval, it's a range of the pH that they are effective. And they have the end point. End point, it's a point where the indicator changes from one color to another color. From the table, we can see the name of other some indicators, the color of these indicators in acidic form, the range of the color change, and color of the indicator in basic form. For example, methyl violet. In acidic medium it's yellow, in basic it's violet, and range of the color of change from 0.0 to 1.6. Or methyl orange, it's in acidic medium it's red, in basic, in alkaline medium it's yellow, and its transition range from 0.1 to 4.4, and other examples you can see from the table. PT. PT of most often used indicators in the acid-base titration. For example, methyl orange has PT 4. We can calculate it from the table. Methyl orange, for example, it has a transition range from 3.1 to 4.4, and PT, its exponent, titration exponent, is equal to the midpoint of the range of the indicator. For example, methyl orange has a range from 3.1 to 4.4, and PT is a middle point, 4. As we see, it's 4. Or methyl red, transition range from 4.4 to 6.2, and titration exponent PT for methyl red is equal 5.5. So is middle point of the transition range. PT of the indicator is the value of pH at which color of the indicator sharply changes and stops to add titrant. There is end point of titration. In the picture we can see the chemical structure formula of phenolphthalein in acidic medium. It is form of the phenolphthalein in acidic medium is colorless, and after titration in X equivalent point in alkaline medium it's violet. Thymolphthalein, chemical structure formula of the thymolphthalein is colorless in acidic medium and blue in alkaline medium. Methyl orange, It's yellow before titration, yellow in alkaline medium, and red in acidic medium, as we see by addition of hydrogen chloride. Methyl red, it's a chemical formula, structure formula of methyl red indicator. Now about the acid-base titration curves. Carries out the decision of the some tasks. The first, the possibility of titration. Second, indicator selection. Third, titrant selection. Curves of acid-base titration express the depends of a change in the pH of a medium on the volume of titrant added. When calculating the pH, three main parameters are taken into account. The first, composition of tetrametric mixture. Second, acid and base ionization constant. Acid and base ionization constant. Third, proportion of titrated substance. Proportion of titrated substance, which is found from this equation. N, its normality concentration of the base, multiplied volume of the base, divide normality concentration of acid multiplied volume of the acid. The residual fraction of the substance being titrated is equal 1 minus P. After the equivalent point, P more than 1, because an excess of titrant is formed in the system. Excess titrant is P after the equivalent point P more than 1, because an excess of titrant is formed in the system. Excess titrant is P minus 1. In the general formula up to the equivalent point 1 minus P. After the equivalent point P minus 1 is used. You need to know four states. Titration of the strong acid with a strong base, titration of a weak acid with a strong base, titration of strong base with a strong acid, titration of the weak base with a strong acid. The first, titration curve of the strong acid with a strong base. For example, 20 milliliter of 0.1 mole of hydrogen chloride solution are titrated with 0.1 mole of sodium hydroxide. Before the start of the titration, pH is concentration of hydrogen proton is equal 10 minus 1, pH is equal 1. When titrating to the equivalent point, the residual fraction is based on 1 minus P. And concentration of hydrogen proton is equal concentration of acid multiplied 1 minus P. pH is equal inverse logarithm multiplied concentration of acid multiplied 1 minus P. If 80 milliliter of 0.1 mole of sodium hydroxide was consumed for titration, we can using this formula, we can find P. P equal 18 milliliter multiplied 0.1 normality of the sodium hydroxide, divide 20 milliliter of hydrogen chloride acid multiplied 0.1 molarity or its concentration of the hydrogen chloride solution, and it is equal 0.9. And pH from the calculation we can find is equal to, if volume of sodium hydroxide is equal 19.8 milliliter, then P equal, and to use this equation we find that volume of the sodium hydroxide with a 0.1 normality concentration, and divide 20 milliliter of hydrogen chloride multiplied 0.1 molarity concentration of the acid equal 0.99, and pH from the equation is equal 3. At the equivalent point we use for example 20 milliliter of sodium hydroxide was consumed, hydrogen chloride with sodium titration of hydrogen chloride with the sodium hydroxide, pH equals 7, Fourth, when titrating at the equivalent point, the excess fraction is based on P minus 1, and POH we find from these equations. Suppose 22 milliliter of sodium hydroxide were consumed. In this case, P equal 1.1 and pH equal 12 from the equation. Second, titration of a weak acid with a strong base. 20 liter of 0.1 mole of acetic acid solution are titrated with 0.1 mole of sodium hydroxide. Before the start of titration, concentration of hydrogen proton is equal in the root of acidity constant multiplied concentration of acid. pH equal, we find from the equation, and constant for acids, equilibrium constant for the acids, we find it's equal 1.8 multiplied 10 minus 5, and pCar for acid 4.74, and pH from the calculation we found is equal 3. When titrated to the equivalent point, concentration of the hydrogen protons is found from this equation. And using this other calculations, we found the results of these calculations. In the third type, at the equivalent point, hydrogen concentration of hydrogen protons is found from this equation, and according to this we find pH. pH using this calculation is found, it's equal 8.687. Fourth, when titrating after the equivalent point, the residual fraction is based on P minus 1, and we use these calculations. Acid-base titration errors. Errors in measuring the volume of solution arise due to inaccuracy in measuring the solutions of the substance and titrant. They consist of the volume of one drop, approximately 0.05 milliliter, with which the solution is usually retitrated, and the calibration errors of meters, its vessels, for example, burettes, pipettes, volumetric flasks, that are subject to deviations, plus minus 0.01, 0.02 milliliter. Errors, there are two types of errors. It's measurement error and indicators errors, with denoted this TE. It's a titration error, TE. It's equal plus minus nu multiplied 100 divided volume V. Here nu is the sum of the drop volume, 0.05 milliliter, and deviations in the volume of the of meters burette, 0.02 milliliter, and pipette 0.02 milliliter, and using this we find the sum of this, it's equal 0.05 plus 0.02, 0.02, it's equal total 0.09, and volume is the volume of the V is the volume of the titrated solution or titrant, and measured by milliliter. First measurement error, for example, we found it from the calculation. Titration error, using this, using the formula, this formula, we found titration error that is equal 0.9%. And when titrating 20 milliliter of the analyte solution, we use this right here, 20 milliliter, and the titration error is equal 0.45. If volume is equal 25, titration error is equals 0.36. Second type of measurement, acid-base error. It's indicator errors. Indicator errors appears when the point of the end of titration, PT of the indicator, does not correspond to equivalent point. There are 4 types of errors. It's proton error, hydroxide error, acid error, base. The proton error is calculated in the percent, and the initial number of protons is equal to the product of normality of the acid and the volume of the solution in V. And at the time of the end of titration, the index of proton concentration is equal PT, titration exponent of the indicator, and PT is equal pH and equal inverse logarithm of concentration of hydrogen proton. Concentration of hydrogen proton is equal 10 minus PT. The final number of protons is determined by the product of the sum of the initial volume and added volume V added during the titration by the concentration of protons. And we write it represented in this equation. The proton error is determined from the proportion taking the initial amount of hydrogen as 100%. Normality and volume of solution is correspond to the 100%, and this equation to titration error of the hydrogen protons, and titration error from this proportion is found. For example, when titrating 25 ml of 0.1 normality of hydrogen chloride solution with the 0.1 normality of sodium hydroxide solution with methyl orange indicator, PT of this indicator is equal 4, and the proton error is found. It's equal from the equation to 0.2%. If it's taken methyl red, for this indicator PT is equal 5. Titration error of hydrogen proton is equal 0.02%. In the case of alkali deficiency and acid overlining, at the end of the titration, an excess of hydroxide ions appears in the solution and the hydroxide errors occurs. Hydroxide errors, we denoted titration error of hydroxide. In the case of incomplete titration of weak acid, some amount of acid remains in solution in molecular form and an acid error occurs. The amount of weak acid in this case is determined by the ratio of the concentration of acid to the concentration of acidic residue, since the titrated acid exists in the solution as anion pool. The error is too large, so you need to replace the indicator. Choosing phenolphthalein, PT, we get titration error for phenolphthalein, which is represented with expressed by percent. In the case of incomplete titration of weak base, at the end of the titration in the solution, its exit remains and the basic error appears. And for example, we can represent it with a reaction, titration error for the base. Its example. The next part of our lecture, it's precipitation titration. Precipitation titration, it is a type of the titration, second type of titration, a special type of titrametric procedure involves the formation of a precipitated during the course of titration. The titrant reacts with the analyte forming an insoluble material, and the titration continues till the very last amount of analyte is consumed. The first drop of titrant in excess will react with an indicator resulting in a color change and announcing the termination of the titration. For example, the titration of silver nitrate with titration of sodium chloride with silver nitrate. Silver nitrate is titrant solution, forms silver chloride precipitation. In precipitation titration method for the chemical reactions, use the following requirements are imposed. For example, an insoluble precipitate should form. The reaction rate should be sufficiently large or to proceed instantly. The reaction should not be reversible. Precipitation must be quantitatively complete. External ions should not be adsorbed by the precipitate, or there should not be paired precipitation. At last, the equivalent point should be easily determined. If non-precipitated amount is 0.01%, then 10-4 mole of solution remains in solution, and from the proportion we find that X equal 10-4 degree. With the same ion change of substance A and titrant B, the precipitate has a decomposition AB. For example, we see it from the equation, and the concentration of titrant B in the solution above the precipitate is also equal 10-4. For example, silver plus silver ion plus chloride form precipitation silver chloride, and titrable substance A, titrant B, solubility product for them for the formed substance AB equal concentration of the anion A multiplied concentration of substance B, and they both equal 10-4. Classification of the method. Precipitation titration divide on argentometric titration, thiocyanometric titration, and mercurometric titration. As we see from the name, in argentometric titration, as titrant solution is used silver nitrate solution. In thiocyanometric or rhodanometric titration, titrant solution used ammonium rhodanate. In mercurometric titration, mercury nitrate univalent. In argentometry used for analysis for chlorate, bromide, iodide, cyanide, rhodanate, and silver salts. When silver nitrate interacts with chlorides, bromides, and iodides, water-insoluble precipitates are formed. And there are, we can see the solubility product for the precipitates of the silver. Thiocyanometry used for analysis of the silver ions. Mercurometry used for analysis of chloride and bromides. And, for example, solubility product for some mercury chloride, mercury bromide salts. Precipitation titration curve. The titration curve in the coordinate axis shows the dependence of the concentration of the substance or titrant in the titrometric mixture on the volume of the added titrant. For convenience, the concentration is represented as a function of P. And from this we found P function A and P for chloride ion. The calculation of the concentration in the construction of the curve is carried out according to the formulas. For example, first, before the start of titration, the concentration of chloride ion is equal to the concentration of sodium chloride, as we see from the equation. Second, in the process of titration to the equivalent point with the calculated in formula 1, first formula, the degree of titration P is introduced, which proportionally reduces the concentration of sodium chloride. And the concentration of chloride ion is equal concentration of sodium chloride 1 minus P. And where P were found from the equation which we used before this. And from this, P for chloride is equal inverse logarithm C, concentration of sodium chloride 1 minus P. And we have an example from this. And third, at the equivalent point, the concentration of chloride ion is calculated from the solubility product of the silver chloride. We found it from the equation. Fourth, in the process of titration after the equivalent point, the concentration of chloride ion is small, and the chlorine is calculated from solubility product of silver chloride, taking into account the increase in concentration of silver by the degree of titration P. It's the example. Indicators of precipitation titration. In the method of precipitation titration for fixing the equivalent point of equivalent point, indicators of the following types are used: precipitating, metallochromic, and adsorption. For example, potassium chromate used in Moore method, silver chromate. Precipitating indicators, such indicators that are extracted from a solution in the form of precipitate in well visible form at or near equivalent points. A small number of precipitation indicators are known. With titrant form colored precipitates, for example, it's a form of indicator with the precipitation. The concentration of the titrant called the indicator is formed from the solubility product of the precipitate, and from this, for example, silver ion plus chloride ions, precipitated silver chloride, and the form of indicator. Metallochromic indicators, in the precipitation titration indicators that form colored complexes with the titrant near the equivalent point. The interaction of the indicator substance A and titrant B in the simplest case can be represented by this reaction. This reaction process in two stages. In the first stage, the composition of the substance AB and the reaction of the anion with the indicator. An equilibrium constant we found from this equation. If equilibrium constant more than 1, towards formation of the complex. If equilibrium constant less than 1, towards the formation of the precipitate AB. Solubility product of the substance AB less than constant of B indicator. For example, solubility product of the precipitate silver rhodanite less than constant of equilibrium of the indicator, formed indicator. Third, adsorption indicators. In solutions ionized, forming easily polarized ions that are colored or change color under the influence of changed particles polarized. The composition of adsorption indicators from protons hydrogen and indicator, negatively charged indicator. The anions of some dyes change their color by adsorbing. It's a determination of sodium chloride with a tetrahedral solution silver nitrate formed silver chloride solid. In the case of opposite charge precipitate and precipitate change color. The adsorption of the indicators occurs on precipitates that adsorb positive ions. For example, with a silver chloride form positive ions. And we have the three methods: Morf, Wolgert and Fayans-Khodakov methods. In each of these methods we use different indicators. For example, Morf method, we use as indicator potassium bichromate. For Wolgert method we use iron chloride. For Fayans-Khodakov method we use adsorption indicators, eosine and fluorescein. And in the table we can see the principle of these indicators and the color which form with the tetrahedral solution. And analyte ions, for example, in the Morf method we analyze chlorides, bromides. In Wolgert method, silver ions, chlorides, cyanides, chromates. In Fayans-Khodakov method is determined bromide, chloride and iodides. Precipitation titration errors. During precipitation titration, during titration of the solution, indicator errors are observed. Total amount of titrant, normality and volume of the solution, excess titrant, volume of substance A plus volume of B multiplied concentration of B, and the concentration of titrant can be determined from the values of solubility product of the sediment of constant of unstable of complex of titrant with indicator. The ratio of excess amounts of titrant to its total quantity consumed for titration multiplied by 100 represented the titration error by in percent, and we find the titration error using the equations. If indicator is complex compound, so we use this equation. For example, titration of 50 milliliter of 0.1 normality potassium chloride with 50 milliliter of 0.1 normality of silver nitrate solution in the presence of 10-4 mole liter of the indicator potassium chromate. At the end point of titration, the concentration of silver nitrate in the solution being titrating is equal to the silver chromate decomposite on silver positively charged silver ions and chromate ions, and solubility product for the this precipitation is equal to multiplied 10 minus 12 degree. And after the calculations we found that the titration exponent titration error is equal 0.28%. and if you increase the concentration of the indicator 100 times, the error decreasing 1 times. And from the equations we found that the titration error is equal 0.028%. It was the last information of our first lecture. Thanks for attention.